Hey guys, this is a project that I worked on 2 years ago and it's working okay, but it's time for an update. So here is a summary. This device is called Scarecrow. It's a motion activated sprinkler that deters animals, because when it detects that an animal is passing by, it sends a stream of water, the animal runs away. I had it for several years and it's working just fine. But maybe it's working a little bit too fine, because sometimes it sprinkles passing people. And so I modified a couple of years ago. I added a circuit that turns it off during the day. And it worked fairly well. It has a battery status. It has a status of the device, whether it's operating or not. It is powered by the same 9-volt battery that it powers this device, but it's time for an update. There are a few improvements to be made. Firstly, the circuit that monitors battery life, it consumes a little bit too much current. It can be done much better, so I would like to take care of that. Another thing is that I would like to add hysteresis to my light detection circuit. It hasn't been an issue because it could be bad. The device could be turning on and off during dusk and dawn, but that was not an issue. Anyway, I will add a hysteresis just to make sure that this never happens. And finally, there is another issue, is that I believe some animals figured this out, that they can actually go into the garden early in the morning, because in the summer the sunrise is very early. And I want to add another feature. I want the device to continue to operate in the morning until I open the door into the garden. So only then I want the device to shut off. So we are going to open the device up, check how it fared the 2 years out in the garden, update the schematic, and see how well it works after all the upgrades. Okay, let's disassemble the device. We have all the gaps filled with silicone, so we'll need to break that seal. Seems to be easy enough. Okay, let's see. All right. So this side looks okay. I don't see any water intrusion. We have the LEDs and the LDR wired up. Okay, fairly tight tolerances here. Okay, this is the barrier that prevents the leads of all the LEDs and LDR touching stuff on the board. And here we have the important thing. So we have the processor, we have some resistors to measure the battery voltage, we have the voltage regulator here, a couple of capacitors for smoothing, and this is a small MOSFET that powers up the device, the Scarecrow. And this is pretty much it that we have in here. So let's draw the schematic and go from there. Let's start with the schematic. So we have a 9-volt battery that is powering our device. And we have a 5 microfarad smoothing capacitor that goes to a voltage regulator, which is a 3.3 volt one. I'm using MCP 1702 voltage regulator, which has a low current consumption at idle, so that's exactly what we want for the battery operated device. I also have 1 microfarad capacitor on the output, so we can see those over here. And so I also have the lead for battery plus that is used elsewhere, and 3.3 volt used throughout the system, but mainly 3.3 volt is connected to the pins of the ATmega 328P microcontroller. So 3.3 volts go to pin 7, 21 and 20, and the ground goes to pins 8 and 22. So that's the ground. Now the device has 2 LEDs. One is for low battery status, which is powered by pin 5. It's a red LED that has a voltage drop of 1.8 volts, and that's why it requires a 220 ohm resistor to limit the current. Another LED that I have is the status LED that shows whether the device is armed, so that it's powering up the Scarecrow. It's on pin 19, and it's a bright green LED that has a voltage drop of 3 volts, and so I actually don't need any current limiting resistor when I'm powering the device with 3.3 volts. It's on for a very little strobe time, and so there is no issue with overcurrenting it. Next is the light sensing circuit that is powered from 3.3 volts. It's basically a voltage divider with a 100K resistor, and the light sensitive resistor connected to ground, and I'm looking at the voltage on pin 28. The most important part of the device is of course the load control, which is controlled by pin 4. Currently I have a pretty large resistor, 22K, going to the gate of a MOSFET. I'm not exactly sure why I chose 22 at the time. Maybe I was experimenting with something else and that was calling for 22K resistor, and then I figured out it works fine, and so I used it. But there is no real reason to use such a high value resistor here. But anyway, because it's a slow speed operation, it still works fine, and it's switching the MOSFET over here, and it provides the control for the load, our Scarecrow device, through the battery plus lead and through its from the MOSFET drain. I'm using BS270 MOSFET, which is working okay for this application, but it's not great because it has a too high gate source voltage that you need to apply to open it fully. Remember that I'm using 3.3 volt in my system, so the maximum voltage that pin 4 can supply is 3.3 volts, and this doesn't open the MOSFET completely, so it provides some resistance. That means that not all the voltage I need goes to the load. It's not a big deal when it's 9-volt battery, but as the voltage of the battery goes down, that can present some issues. This is something that I would like to fix. It can be fixed by using a more expensive MOSFET with a lower gate source threshold voltage, or we can try to do something else with our circuit. We'll talk about it later. Last but not least, I have a battery monitoring circuit that takes a battery voltage and through a high resistance voltage divider, 300K and 22K, provides voltage to pin 27 where it's measured. The problem with this is that 300K is not high enough to make the current low enough so that it doesn't drain the battery excessively. This arrangement draws current all the time, and we basically drain the batteries very slowly, but still with such arrangement this circuit will drain the battery by itself in about 5 months. So that's not very good for the battery operation. So this is something that we need to fix. Okay, so let's make the following modifications. Firstly, we will not power the light detecting circuit from 3.3 volts all the time. Instead, we are going to use pin 23 to power up this circuit only when we need it. Secondly, we will completely overhaul our load control and the battery monitoring by combining these two circuits in the following way. So we'll have let's say pin 24 that controls the gate of one MOSFET also BS270, and it's connected using 1 mega ohm resistor directly to 9 volts. and only then its drain is connected to our final MOSFET that controls the load. Okay. The source of the first MOSFET is not connected to the ground directly, but it will be using a 22 kilo ohm resistor. And only at that point we are going to use pin 27 to check the battery voltage on that. So the whole thing will work in the following way. If the pin 24 is on, then this will ground this the gate of the second MOSFET, almost grounded, and so the load will be off. At this point we also will have the voltage divider 22K and 1 mega ohm supplying some voltage to pin 27 where it can be measured, so it will provide us the battery status. However, during the night time, pin 24 will go to the ground, shutting down this MOSFET, and straight battery voltage will go to the gate of this MOSFET, the output MOSFET, and will turn on the load. And this will work pretty well for us. So what we are going to do now is to assemble this on a breadboard and check how well it works. Okay, here is the money shot. We have this circuit assembled on a breadboard. I have a 3-volt battery. They're connected to the gate of this first MOSFET with a button. The button is not pressed right now. And this means that 9 volt that's coming from this line is powering the LED and the precision 47 ohm load. This is basically 10 470 ohm resistors in parallel, and we have it working. If I press the button, the LED stops being lit. And the MOSFET, the final MOSFET, is fully on because, as we see, we have 9 volts and 190 milliamps, as should be when you have a full 47 ohm load completely on. So this circuit just works from 3 volts at the gate. Everything is perfect. The last modification that we'll make is to add a DOS switch. So we will use a pin number 6. Through a resistor. Go to the switch. And we will also supply the ground also through a resistor, so that we can sense whether the pin 6 is grounded or not. Okay, let's take a look at the program. So in Arduino IDE I have a sketch. First we include the lower power library so that we can put the controller to a deep sleep. The next section is just the definitions of the pins that we are going to use. Global variables, whether it's a night, whether the door was open, and whether the device is armed. This is the variables that we'll use in the loop function. In the setup, we just set up the output pins and the values on them. If necessary, we enable the serial communication line. And then the main function is the loop function. First we wait for 4 seconds and sleep, consuming almost no power. But then when we wake up, we are reading the value from the light detecting resistor. then we can check the battery value, whether its voltage is too low or not. And remember, we can only do that when the device is not armed. If the battery value is too low, then we enable our red LED to report the battery status. Now we need to decide whether it's a night or day depending on the LDR value, and here how we implement the hysteresis I mentioned before. So if it is a night variable is set before, then we will use one threshold value, and when the isNight variable is false, then we use a different value, and this way we can maintain the hysteresis. Now we need to check the whether the door is open. Well, if it's night, it doesn't matter, we set it to false, but when the day comes, then we need to check the value on the door read pin, and if it is, then we set the was door open during the day to true, and you see that it will remain true even if the door is closed afterwards. So now that we have two variables set up, isNight and the door variable, then we can decide whether the device is to be armed or not. Of course, it happens if it's night or when the door was not open during the day. Here is a statement that can send debug information to the serial line. Now we are going to use the green LED to flash the status of the device, and if it's armed, we will flash it 3 times. If it's not armed, then we will flash it only 1 time, and then we will use a control pin to turn on or turn off the load, depending on whether the B is armed variable is true or false. And last but not least, remember that we could have turned our red LED to report the battery status. Now it's a good time to turn it off. And that's it. That's the whole program. So now what we are going to do, we are going to upload it to our controller, which is what I have here, put on a breadboard connected to the FTDI from SparkFun, and we'll see what happens. So I'm going to press Ctrl U and it will start programming, and then after it's done, it says done uploading, thank you, and what we see, the MCU starts working. It's not getting any input because it has nothing connected to it, except I have the LED that sometimes blinks every 4 seconds. Now what we need to do, we need to take the chip out and put it back in our device and see if that device operates correctly. So is it time to put the chip in and pack it up and put it in the field test? Of course not, we need to do the bench testing. So I have the power supply at 9 volts, and then going through a multimeter set to 20 milliamp range, and we are going to power the device and see what happens. So I'm going to turn on the device, and every 4 seconds we have a 1 blink, which means that it considers it's a daylight, and the device, the target device, the Scarecrow, is not supposed to be powered on, and which we can confirm because I did wire this white LED as a load. So now it's daytime it's not working. But let me just cover the LDR, and we immediately see that this LED starts blinking 3 times, and the white LED, the load, lit up. So our device is working. If I release it, then it turns off the white LED and starts blinking slowly, just 1 time. And the consumption is about 0.01 milliamp, which will last for a long time. So one thing that we need to test as well is the battery status. So what I'm going to do, I'm going to lower the voltage of my power supply and see when the battery status, this LED, will come on. So now I'm 8 volts, still nothing. Now 7.9, 7.8, 7.7, and we see that 7.7 volts, both LEDs light up. So the battery status is saying your battery is low. So everything's good. We haven't checked the door circuit yet. It's completely disconnected, so it's out of the picture yet, but we'll do it in a moment. Okay, to test this door switch operation, I have a jumper wire stuffed into those connectors, and what happens now is that it thinks it's a daytime and the door was open previously, so it continues to operate like it's a daytime and the load device is not armed. You see that white LED is off. So now what we are going to do, we are going to cover the LDR so it switches to the nighttime, so it lit the white LED. Okay, so now because the door switch is closed, even if I release my finger, it's a daytime, but the door was not opened, so it will continue to be armed. And this is what we actually see. It continues to do the 3 blinks and the LED is on. So now what I'm going to do, I'm going to remove the jumper wire, which is equivalent to door opening, and it should switch back to the daytime not armed mode. So this LED is off. Perfect. It all works. We have an exhaustive test. All we need to do now is to assemble it completely, put it all together, and put some silicone in the places where you don't want the water to get in.